sections. So it should be possible to color the graph in finitely many colors. Yeah, right. The chromatic number of the graph, of this graph, let's just say the graph is gamma, edge of gamma is phi of gamma finite. Does this imply that there's some finite coloring? That was the question. And Katznelson more or less answered it on the spot. I mean, he heard the question and he answered it on the spot, realizing that it turns out that this question is equivalent, that this question about lambda is equivalent. This is equivalent, this property of the chromatic number being finite, this is equivalent to lambda not being, that lambda is not recurrent, not a compact recurrent. In other words, there is some action on a compact space, and you cannot find in lambda and no point in this particular space returns to itself under lambda. Now, Katznelson found this example. It turned out that this example that he found, to prove that it was not compact recurrent, Katznelson found a rotation of alpha belonging to the one torus and a lacunary I may have gotten this, I may have confused this with lambda is still may have a confusion here. Straighten that out. At any rate, this was the problem that raised the question. The question is, does Bohr recurrence imply compact recurrence? In other words, would it always be the case that if you found an account of something which is not, compact recurrent, then already there must have been an example which is not Bohr recurrent. So that's the question. With the background. Now my next question, you can call, which is part of a series of questions we can call dynamics on the integers, or dynamics on, let's say, on the natural numbers. And this includes a question that, a very famous question that Sinai has thought about also. But so let me take a related question which people are not, which is not that famous, and then I'll go to the more famous question. Basically, we're thinking of transformations on the integers. Here the so the particular question I want to take is let 11 goes into 15, that goes into 21, that goes into 30, that goes into 45, and so on. Now I can ask, more an elementary way of formulating the question is, are there as many even numbers here as there are odd numbers? There's a limit. There's a probability of a number here, like a normal number, if I were to put a decimal point in front of it, that this is in fact a normal number. Let me do that. And you're right. Because we should be familiar with this notion of a normal number, which has to do with the statistics of given some sequence. And I asked whether the statistics is like the expected statistics when you toss a coin. Now, one thing you might say, well, maybe this is ultimately periodic. I mean, the worst thing it could be, the furthest away it can be from behaving like a coin tossing sequence is to be ultimately periodic. Well, that is not hard to show, and it can be shown by looking at this problem in a certain way. With the ergodic system, there are points that are not ergodic, and not generic, but almost every point is generic. And the question is whether this particular point, because of the rationality, I mean, you might say, well, why should this be better than any other point? And it may be the fact that this represents a rational orbit in this system. Now, what is this system? Now, here I have to use